Okay, welcome back. So I fixed my slide a little bit because I realized that I should put the word radiate up here. Waves radiate. Light radiates out in all directions. You can imagine that best with maybe a candle flame. A wave is really, as we're going to see, it is a radiation that comes out in all directions, but it doesn't always appear that way because of positive and negative interference. So this is here's a little drop coming off, and it's dropping onto the surface of the water. And the water is the medium, and the disturbance is traveling through. And it's the energy, really, of the disturbance that we're concerned with. And so these concentric rings are supposed to be these concentric rings of the wave spreading out. And it's going to spread out in all directions. The circle gets bigger and bigger and bigger. What is that circle made of? Why does water do this? Well, different media do it in different ways. The jello that I'll show later is going to move in a very different way than water would. And it has to do with the ways that the medium is held together. Now, water is held together by hydrogen bonds, which are, it's not a full bond, it's not a molecular bond, it's just an attraction because water has a negative side and it has a positive side. It has an oxygen here, which is slightly negatively charged. It's big, it holds on to the electrons that they're sharing more than the hydrogens do. So that leaves the hydrogens kind of looking for a little bit more electron action. So they tend to line up and be attracted to the next over oxygen thing. And these are called the hydrogen bonds. And so that's what holds the surface of the water together. So what happens when we hit water is a particular water molecule. If you went down to the very molecular level, you would see a particular water molecule is hit with a force or is disturbed in some way. And then different parts, its attraction, it's the surface tension that holds this all together, is going to cause it to cause different water molecules to also move. And then when they move, they send out a wave in all directions too at their location. Now, I don't show water molecules down here because I just got lazy, but each of these things, the only way this wave moves in a water wave is by disturbing other water molecules. It gets down to the molecular level. Things like different liquids have different viscosity. The viscosity is a function of the molecular and chemical makeup of the liquid. How fast a wave can travel through a medium is related to its viscosity, and it definitely has to do with when I disturb one, how likely is it or how strong a pull does it have on the very next molecule over. So when you get down to this is like the wave on a string. With the wave on the string, we see individual beads. In a water wave, think of those as individual water molecules that pull on the next water molecule, probably with hydrogen bonds. That this is how these things are moving and disturbing each other. So that means that as each wave spreads out, it is in fact individual little waves spreading out, because once a water molecule gets disturbed, it makes a little wave, a little circular wave that then radiates out in all directions. Now, this isn't what we see when we look at wave tanks. You may have seen these in science museums. I'll be including as an extra credit activity how you can do this in a baking dish at your home, similar to this diagram here. You need to glue a pencil onto a pencil, so it's not quite shown here, but this is kind of a T-like thing that they're using to disturb the wave to make their straight waves. So if you've been to a science museum, you may have seen these water tanks, and we definitely use these in physics classrooms in high school. I think I can have some video for you of Walter Lewin using one in the MIT freshman physics classroom, where we have something like this oscillating paddle that helps us make these horizontal waves, because we'll look at that. So what they're doing when they make these horizontal waves are really helpful for helping us explain what light is looking like when it goes through things and why it behaves the way it does, and what led Huygens to believe it was a wave. They disturb a whole bunch when they will oscillate this paddle so it goes up and down, shaking the water. And what they're doing with this paddle, here's the red paddle, is they're disturbing a whole bunch of water molecules in a row at the same time. They're pushing them up and down. They're all experiencing the same force, and then they're all communicating that disturbance out. Now notice it goes in both directions. It goes out this way and it goes back this way. But we're kind of we're more concerned with what's going out this way. And we don't pay attention to the fact that it is radiating out in all directions. It really, really is. And if you look above, when you have your own, when you look above and below, you'll see a little bit of turbulent weirdness. You won't see necessarily this really beautiful wave thing, which gets to how this is really just droplets of water that are being disturbed. And this is the part I think we did the best with under the tough conditions we had in class on Wednesday, which is this wave moving up and down is moving individual water molecules. So think of a water molecule in each of these four things, and each of those four water molecules is going to disturb all the water molecules around it, and there's going to be a concentric ring coming out from each of those water molecules based on the disturbance. This is where we bring in the positive interference and the negative interference. And it should be positive interference, destructive, I put negative interference, it should be destructive interference. Constructive and destructive. I'm going to pause right now. Oh, I'm glad I caught that. So it's not really called positive and negative interference. It's not. It's constructive interference, which is in phase, or constructive interference. This is perfectly constructive interference, which is in phase. When you are perfectly constructive, that means that you are absolutely lined up. Ella and Jason start at exactly the same time. They go down at exactly the same time. Glenn will feel the down is twice as big. He will feel the up as twice as big. So that is perfectly constructive interference, which is in phase. Perfectly destructive interference is 180 degrees out of phase. I was so pleased that you guys had those terms on the top of your on the tip of your tongues when we were ready to start. That was great. So in perfectly destructive interference here, Ella starts before, but when Jason starts, he is 180 degrees off of Ella, and Glenn will feel nothing. Both waves are still coming in. If you ask Jason and Ella, they're still working hard, sending waves down to Glenn, but Glenn will feel nothing, and if they're perfectly aligned, and if this is light, it will be dark. So this is perfectly destructive interference, which is 180 degrees out of phase. What gets kind of interesting is the interference. Some yes, some no. Where they're headed up, they just add together. They just add together. Notice that Glenn will never feel anything totally at 2. And the only time he feels 1 is when we just have Ella, because here, even though they're not totally out of phase, they're a little bit out of phase, and he never quite feels the same oomph as he did when they were as either Ella by herself with nothing from Jason. Everything else is damped down. This is called damping, which we haven't talked about at all. But when you squish that wave down, it's called damping. And so Glenn's going to feel a little bit, but it's going to be less than either Jason or Ella, even though it's not perfectly destructive. Sometimes it's positive, sometimes it's negative, but it's going to be down. Okay. Why we see these very parallel looking lines has to do with that interference that's happening between the points in the up-down way that isn't happening in the left-right way in this scenario. We saw that also when you had your resonance, when you worked on resonance and you were adding waves. As you add the waves, there's this little bit of error that gets kind of blah, but it's less noticeable. The more you've added together, the bigger this amplitude is, the more it looks like just one wave going down the line. So as this wave resonates, as you add constructive interference, it really starts to look like just one wave, and you really just forget about the little wobbles on the edge. That's what's happening. And if we added those up, we would get something which is more like this. We have like a rigid line going down. And if we connected up so if we looked at this as if the dark is the down and the white is the up, then if we add up all the downs and this is where we would see all the most down. And then if we put a white thing in for where we would see the most up, then pretty soon this is the wave that we're seeing. And it's because the top bottom thing here cancels each other out. This wave is going to appear to be horizontal lines traveling in the right direction. When that set of waves hits something here, I'm going to pause for just a second and insert something. Okay, I'm going to have to return in another segment, so I'll be right back. This is segment number 2. I'll see you in segment number 3.